So you record
Yeah, so I'm not. I don't give this to you. I'm gonna give this to you. This is on this iPad.
No, I never took it.
Okay.
I just steal your iPad. You heard me? I just steal it. Where is
Look at here.
So remember, one of the things we said is that we could calculate relative and absolute bioavailability using urinary excretion data. We said that for absolute bioavailability, today we're focused over here, just to let you know where we're at. So we said that absolute bioavailability, we can look at the AU infinity value for the PO dose divided by the dose administered PO over the AU infinity after an IV dose divided by the dose IV. And then we said for relative bioavailability, using urinary excretion data, we could look at relative bioavailability is equal to AU infinity AU infinity for the test product divided by the dose of the test product. We call the test product just A, okay? That's what we call it before. And we said that we could look at the AU infinity for the reference standard B divided by the dose of the reference standard B. So we said that we could use urinary excretion data collected over here to determine absolute and relative bioavailability. Now we're going to use urinary excretion data. We still have some constraints that we talked about before. You know, we're going to have to make sure we collect for at least 7 half-lives. We're going to have to collect all of the samples, especially if we're trying to determine AU infinity values. So we can't miss a sample if we're doing cumulative urinary excretion. We need to make sure that the subject or the patient completely empties the bladder as much as possible for each sample collection. So I pointed out before that a lot of times, you know, that makes a urinary excretion study kind of hard to do in elderly folks because sometimes the geriatric population has more difficulty completely emptying the bladder. So then we also say that there are certain things you cannot calculate in urinary excretion data, like volume of distribution. To get the volume, we need some data from the plasma, you know, whatever. So we can't calculate volume of distribution or clearance, total clearance, if all we're looking at is urinary excretion data. So a few days ago, we talked about the fact that if we're looking at urinary excretion, where AU is the cumulative amount of drug excreted in the urine. So AU infinity is that final total amount of drug. Then if we look at AU as a function of time, we said that curve is going to go up and it's going to plateau off at some point. And that final value over here, when it plateaus, is AU infinity. Okay, so that's the value on the y-axis, AU infinity. That's the final total amount of drug excreted in the urine, AU infinity. Okay. So the cumulative amount of drug in the urine is going up, and then it'll reach its final value. So we want to make sure we follow urinary excretion of drug for at least 7 half-lives, so we can get an accurate determination of AU infinity. If we don't follow it for at least 7 half-lives, then when we get ready to treat this type of data mathematically or pharmacokinetically, then our AU infinity value is going to be too small and it's going to throw off all of our calculations for Ka and KEL and that kind of stuff. Okay? So, the equation that describes urinary excretion in the urine after an oral dose, or any route that requires absorption, the equation, and you don't need to memorize this equation. If you need it, I'll give it to you. That's a long equation. I don't use it that much myself, but we will be using it in laboratory today and tomorrow. Okay. So the equation says that AU, the cumulative amount of drug in the urine, is equal to F times the dose times KU. Let me put some time signs there. F times the dose times KU divided by KEL, and this is where it gets kind of wicked. That's times 1 minus 1 over KA minus KEL. Make sure I get this right. Bang, bang. No, minus 1. And then that's all times KA times E to the power negative KELT minus KEL times E to the power negative KA times T. Okay, so the only reason I have to remember this is that I looked at it before I came to class today, okay? So I'm saying to you, no, I'm serious. God, you know, we don't use this, I don't use it that often, but this equation governs the cumulative amount of drug excreted here. We had a similar equation, it wasn't quite this long for an IV bolus dose, when we looked at the amount of drug in the urine versus time. So let's get the hierarchy correct, okay? Because in laboratory today, I told you we're gonna be simulating some data. So I'm gonna make we're gonna choose a value for dose for F. You know F is the absolute bioavailability now. KU, this is F times D times KU in the numerator over KEL. I'm writing kind of small because it's a big equation, so let me say yes.
Is this AU infinity too on that one?
This is AU.
No,
AU.
I'm talking about that one.
Here?
Yeah, what's that?
That's this final value. I just drew a dot. That's on the y-axis.
What I'm saying is on that's in that A. What's that? Is that M or what?
Where, here?
No, on top there.
Up here?
Yes, is that L?
AU infinity, I'm sorry. I'm just trying to show that AU infinity is the same value over here on the y-axis.
Okay.
Does that make sense?
AU.
This AU infinity where it peaks out is this same value over here on the y-axis. That's what I'm trying to show. Okay. So 1 minus 1 over KA minus KEL, and that's KA times E to the power negative KEL times T minus KEL times E to the power negative KA times T. So make sure that in this numerator right here, the only place I see KU is in the numerator right here. Okay, KU. Okay, the rest of those, that's KA, KA, and KA right there also. So don't get the KAs and the KUs mixed up because my U's are not that distinct. Okay, KU. The first order rate comes from urinary excretion. That's this KU right here. Okay. So let's look at a couple of things. One is let's look at the way you're going to have to do the math. This is 1 minus the product of these two things. I just call this X and I call this Y. So that's 1 minus X times Y. In laboratory today, when I get you to do the calculation with this equation, don't subtract 1 minus X and then multiply that times Y. So that's why I'm trying to get my brackets of parentheses in order. This, based on hierarchy, is outlined here. Is 1 minus the product of X and Y. Does that make sense? Mm-hmm. Don't make a mistake of subtracting X from 1 and then multiplying that times. That wouldn't be right. And then that whole thing that's in these brackets here is multiplied times F times dose times KU divided by KL. So make sure you get your hierarchy correct, first of all, or you're not going to get the right value for AU. So that's one thing. Another thing to recognize here is that normally KA is greater than KEL. Well, let me go step back. If T equals 0 and time 0, how much drug will we, forget the equation for a moment. In this model here, when T is equal to 0, how much drug will we expect to see over here? And time 0. That's right as soon as we give the drug. 0. We know that intuitively, right? Well, see if you can make this equation say the same thing. If I put T equals 0 here and T equals 0 here, I should see that AU is going to equal to be equal to 0. See if you can just take 15, 20 seconds and you can reconcile that in your head.
Yes, sir.
When this T and this T are 0, then this is going to be 1 minus 1, right?
Zero.
Right? I'm saying if that exponent is KL times 0, then all of this KA times e to that's equal to 1, right? This is equal to 1, so that'd be 1 minus 1 is equal to 0 times this x component here. That's 0, right? Right? X is not 0, but x times y will be equal to 0, right? So I have 1 minus 0.
One.
I'm not saying that right. Oh, wait a minute, I'm doing something wrong. I'm seeing something wrong. Because this shit, x minus 1 at times 0, help me out, y'all. At times 0, x minus y should be equal to, x times y should be equal to,
Are you still multiplying 0 times that 1?
I want this t to be 0 and this t to be 0. So what I should have in this numerator is K-A over K-L, 1, yeah. This numerator should come out, right here should be K-A over K-E-L. So I should have 1 minus 1. Help me out. K-A. I see it now. E to the power of K-E-L times T is equal to, when T is equal to 0, that's equal to 1, right?
Yeah.
When T is equal to 0, E to the power negative K-E-L times T is equal to 1. I think I said something else.
Yeah.
And when T is equal to 0, E to the power negative Ka times T is equal to 1. Right?
Yeah.
So at time 0, follow me on this, at time 0, then this would be Ka minus Kel. At time 0. Does everybody see that?
Yeah.
At time 0, this y component here would collapse to Ka minus Kel. At time 0. And at time 0 only. Is that okay? Brandon, is that okay? Negative. Okay, I don't want to just say it. I want you to see it.
Yeah.
When I write the test, you're just trying to memorize. I want you to see it. That when I put t equals 0 in this equation, that this y component reduces to Ka minus Kel at time 0. If you're just trying to memorize that, you don't see it now. I'm tricky. Come test time. Okay. So the y component at time 0 would be Ka minus Kel, but that's times this 1 right here. So Ka minus Kel times this 1 would be Ka minus Kel in this numerator at time 0. So Ka minus Kel over Ka minus Kel is equal to 1. So I'd have 1 minus 1 at time 0. This would collapse to 1 minus 1, which is 0. 0 times this would be 0. So you've already told me at time 0, the amount of drug over here in the urine should be equal to 0. So the equation confirms that also, with a little bit of work and a little bit of vision. You can see that at time 0, this equation also says that AU is equal to 0. So I'm going to write that. At t equals 0, the amount of drug in the urine is also equal to 0. That's the conclusion of what we just talked about. So I want you to be able to see and recognize and mathematically show that at time 0, this AU is equal to 0. Don't just memorize that, sports fan. If you have the equation, you have to be able to show that, like we just talked about. And then at time infinity, at t infinity, then AU would be what we call AU infinity. And that's equal to, let's look at the same equation up here. If I put time infinity, in other words, something greater than 7 half-lives. So we ain't gonna be waiting around until the second coming. So it's something greater than 7 half-lives for this time right here. So let's say the half-life is equal to 3. The half-life is equal to 3 hours. then if I put a time in here greater than 7 times 3 is 21, 21 hours or greater, I should have reached pretty much, it's gonna be close to my AU infinity value. So AU infinity, look at this equation. At time infinity, can't you see that this value and this value are gonna approach 0? They're gonna be very small. At 7 half-lives or greater, this term is gonna be small. And this term is gonna be small. They're gonna have approached, they're not gonna go to 0, but they're gonna be very small. So at time infinity, this y component right here, okay, is essentially equal to 0. It's not gonna be, it's gonna be a positive number, but it's gonna be so small that 1 over Ka minus KL times y, x times y is gonna be essentially 0. It's gonna be a real small number. It's gonna be much less than 1, let's put it that way. So 1 minus the product of x and y is gonna almost give me the 1 back. It's gonna be 0.99, 0.9 something. Does everybody follow what I'm saying?
Yes.
At infinity now, we've already talked about the case where we're 0. You know, all the AU values are gonna have to occur between time 0 and time infinity. Okay. That's where all of these values are gonna be calculated, between 0 and infinity. At time infinity, AU is equal to AU infinity, and I hope you can see that's just the same as F times the dose times KU divided by KEL. It's gonna just collapse to this part out here. Because you're gonna have, you're gonna have 1 minus some small number, x times y, which is essentially 0. So that's gonna be F times dose times KU divided by KL times 1. Okay. Which is equal to F times dose times KU divided by KL. I just put this 1 here for emphasis. All of this x times y is gonna be so small, so you're gonna have 1 minus a real small number. So that's this 1 right here. So I just put that there for emphasis. So you still get F times dose times KU divided by KL. That's AU infinity. Now just like when we talked about the IV situation, don't make AU infinity something that's foreign to us or foreign to AU. AU infinity is just the final total value for AU. Like I tried to show here. These are AU values on the y-axis. When I reach the highest final amount at 7 half-lives or longer, that highest amount of unmetabolized drug excretion in urine, that final cumulative amount, we just call it AU infinity. It's still an AU value. It's still an AU value. It's still on the y-axis. So I don't want you to see AU infinity and AU as something that's totally different from each other.
Because it's in the equation right there. Because it's in the equation, like right before.
In other words, this equation, this part, I can substitute AU infinity for this part of the equation. We still be dealing with the same thing. AU infinity is just the final value that we get for AU after 7 half-lives. So that's what I'm trying to show here. You know, at time 0, this equation, AU would be equal to 0. At time infinity, AU, we're just calling it AU infinity. It's still an AU value. It's just the final total amount of drugs created in a year. Is that okay?
Yeah.
All right, very good. Okay, so how do I say this? So when we're in the, I know what I want to say. Remember we said that in the normal case, not the flip-flop model, because we had a case where Ka is greater than KEL in this model, and we had a case where Ka was less than KEL. So I don't want to talk, we're not going to deal with the flip-flop model here, okay? In the normal situation where Ka is greater than KEL, then if Ka is greater than KEL, then see this second circle term right here? Just like before, when Ka is greater than KL, that's a normal situation. That's what we see most of the time, that this value is going to be greater than KL. Then in this equation right here, when Ka is greater than KL, then when we get in a so-called post-absorption phase, because even though we're looking at urinary excretion data, we still have drug in the plasma, right? It's getting in the urine because it's coming from the plasma, through glomerular filtration and all that kind of stuff. So even though we're looking at urinary excretion data with this equation and what we're talking about today, we still have drug in the bloodstream. Does that make sense? This drug over here is coming from drug in the body. It ain't just magically appearing over here, okay? It's being excreted by way of renal excretion, which you know all about from your physiology and pharmacology classes and stuff, okay? So this AU is being excreted into the urine, okay? So we still have drug in the body, right? That drug is gonna still see an absorption phase and a post-absorption phase, right? Here, I'm talking about here. I ain't talking about in the urine, you know, I'm saying in the body, in the plasma, we're gonna still have an absorption phase and a post-absorption phase, right? And this is the model that applies. So by the time we reach the so-called post-absorption phase, this second term right here that I have circled is very small compared to this first term. Just like we talked about before, because if Ka is greater than KL, this second term right here is approaching zero faster than this first. Okay. So by the time the that's right, the post-absorption. If we're not in the post-absorption phase and we want to calculate an AU value, we need the whole equation. But in the post-absorption phase, let me write that. In the post-absorption phase, AU could be described as AU infinity. I'm just making a substitution here. For F times those times KU divided by KL. AU infinity times 1 minus 1 over KA minus KEL times E to the power of, I didn't write that down, times KA times E times KA times E to the power of. Is that true? Did I do that right?
You said this is post, okay.
1 minus. Is that okay? This second term, in the post-absorption phase, that term is so small, so all I have in the post-absorption phase is this right here. So this equation is always true, but we can shortcut if we're looking at urinary excretion in the post-absorption phase. In other words, if we've gone past Tmax. You say, well, how do you know about Tmax? Well, we still got Ka and KL, and we know an equation that we can calculate Tmax in the bloodstream. So if we're on the other side of Tmax, we're in the post-absorption phase. And we can use this equation to calculate urinary excretion. This equation is still true, so I'm not saying that this equation doesn't apply. But the reason I'm shortcutting it right here is because we can take this equation and linearize it. It's not in the form of y equals mx plus b now. But if we multiply through by AU infinity, multiply through the brackets, do some rearrangement or whatever, I'll show you the resulting equation.
I have a question.
Yes.
Pardon my absence, but I just want to know, what does 1 minus 1 over Ka minus KAEL mean? Like, what is that?
It don't mean anything other than it's used to help. It's used to help us calculate AU.
Oh, okay.
It don't mean anything, at least that I'm aware of.
Because I know, like, the last two sections we talked about absorption and post-absorption. So I'm like, okay, what is this section?
No, we just need it in this equation to help us calculate the KU.
Okay.
Not KU.
AU. Yeah. Okay.
Okay. It doesn't have any distinct. The question is, for those that may not have heard, probably didn't hear, is what does this 1 over KA minus KL mean? Okay. It doesn't mean anything except that it's used to help us calculate the AU value. Okay. So that's part of it. If we leave that out, either here or here, you're not going to get the right value for AU. Okay. Yes. Yes.
So in the post-absorption phase, the formula you wrote, so you ignore the second portion.
Yes, but I told you why also.
Yeah.
Yeah, I told you why also, so we ain't ignoring it just for the fun of it. I want us to be able to explain that and understand why. Now in the post-absorption phase, this equation is still true. But what we can do here, what I'm gonna show is that, and I want you to see if you can do this on your own, see if you can multiply through the brackets, I'm talking about for homework or whatever, and see if you can come up with an equation that shows that the natural log of AU infinity minus AU is equal to, I need to cheat, okay. Is equal to the natural log of, let's see if I got this right. AU infinity
When does it get to this?
times KA
This is 31.
over KA
Kind of makes sense so far.
minus KEL
This one is ready. We have it ready. So
Because of the
it's
those times K.
minus KEL times T. Oh man, that's a bunch. Okay, let me tell you what I want you to do.
So we have to number.
See if you can go from here, this equation right above this last one I just wrote, see if you can get from here to here. Just for practice. See, if you, so the first thing you're gonna have to do is you're gonna have to multiply through the right hand side by AU infinity. So you're gonna have AU infinity times 1, then AU infinity over, well the easiest thing to do, I guess inside of this equation here, you have Ka times e to the power negative KL times t, where this 1 is right here. I'm saying before you multiply, this is what I would do. This part of the equation right here, Ka times e to the power negative KL times t, is just the same thing as having this in the numerator. Do I follow that?
Yes, sir.
You do?
You
There
said
you go. John said yes, sir.
I'm like, oh.
I'm saying you don't have to do it that way, okay? But the bottom line is you're gonna have to multiply 1 over Ka minus KL times what I got in parentheses right here, and then that's gonna be subtracted from 1. So see if you can go from here and see if you can come up end up with that equation, just for practice. So the equation you're gonna have right before this final equation, you're gonna have an equation that says that AU infinity minus AU, this is before you take the logs. You're gonna have an equation that says that AU minus AU infinity is equal to AU infinity times KA over KA minus KL times e to the power negative KL times t. In other words, I'm trying to get you to see what the equation is gonna look like right before you get to the final step. The equation right before this one is gonna say AU infinity minus AU is equal to AU infinity times KA over KA minus KL times e to the power negative KL times t. Then when you take the logarithm of that, you're gonna end up with this one. Questions? Okay, it's just like when you had C is equal to C0 times e to the power negative KE. I'm just going backwards now. So here we go. This is after the IB roll stuff. Class like that. So I say, see if you can go from here to here. The log of C is equal to the log of C0 minus KEL times T. All I'm doing is going backwards. So so here in this case, I hope you can see that the equation right before this one had to look like this right here. The equation right before this logarithmic equation had to look like this one right here. So all I'm doing is I'm using that same approach here. The equation right before this logarithmic equation had to be an equation that says that AU infinity minus AU is equal to AU infinity times. The logarithm wouldn't be there. AU infinity times KA over KA minus KEL times e to the power negative KEL times t. Right before I got to this equation. So see if you can reconcile that. Any questions about what I'm asking you to do? So, here's what we can do with this last equation here. And we're gonna do in laboratory today. So make sure you bring some logarithmic, semi-logarithmic paper also. Because we're gonna do some graphing based on this equation. This last equation. Now, when does this equation apply? When is this appropriate? Post-absorption phase, absorption phase, or both? Post, because it came from the output. Exactly right. So this is only true during the post-absorption phase. But look here, if we take that final equation that I just wrote, that I just circled, and we'll actually do this in laboratory today. And if you guys, today and tomorrow, and if you work with me and you understand, take from this lecture what I want you to do, then we shouldn't have to be in laboratory for 3 hours. Okay. If we take this equation is in the form of y mx b. So, same old script as before, just some different characters. I'm gonna say compare to the log of C is equal to the log of C0 minus KEL times T. Do you see the resemblance? Instead of the log of C, I got the log of all this stuff right here. Instead of C0, I got all this here, AU infinity times KA over KA minus KL. KLT are the same. So what I want you to see is that if I take that urinary excretion equation and I look at a plot of the logarithm of AU infinity minus AU on the y-axis, sports fans, on the y-axis, because that's what's in my y position. Now, of course, I can do this, we can do in laboratory, we're gonna be doing this on semi-log paper, so I'm not gonna have to take the natural log of AU minus AU. It's gonna be on semi-log paper. So just like you can plot this on semi-log paper, you didn't take the natural log of C when we did on semi-log paper, you just plotted C, right? Hold on to that concept, sports fans, because the same concept that you use to plot this type of data, you're gonna be using to plot this type of data also. Okay. So instead of C, you got AU infinity minus AU. So if AU infinity was equal to, I'm trying to keep it simple. If AU infinity was equal to 100, that's 100 milligrams. But at some time before infinity, AU is equal to 10 milligrams. Because AU is increasing, right? So let's just say sometime, before AU infinity, the AU is equal to 10 milligrams. 10 milligrams. Then AU infinity minus AU would be 100. Let's just say 100 milligrams. Minus 10, that'd be 90. So on my semi-log paper, I just plot 90 milligrams. I don't plot the logarithm of 90 on my semi-log paper. Okay. So when I do that graph for AU infinity minus all of those AU values leading up to AU infinity, okay, we're not going to be plotting this data here, which is curved. When we plot it according to this equation, then we're going to get a straight line. So we're making this graph, we're converting it to a graph that looks like this. Okay. And the slope of that line, anybody, the slope of that line based on this equation should have a value of what?
Negative KL.
Negative KL. Don't come Monday night and trip out if you see something like this. If you see, by the way, this is another version of a so-called sigma minus plot. I told you that when we were talking about IV, that sigma minus plot of urinary excretion data. Okay. When we look at AU and same thing is true after an IV dose. Okay. So the slope is equal to negative KL. You calculate the slope just like you've already calculated. Always calculate the slope. Slope is equal to negative KEL. Now this is what throws students sometimes. When we had an IV bolus dose, this intercept here was equal to AU infinity. Because for the IV, when we gave an IV bolus dose, we said that urinary excretion was, this is a sidebar, sports fans, for an IV bolus dose. IV bolus. This is sidebar, okay? For IV bolus dose, we had an equation that says that the logarithm of AU infinity minus AU is equal to the logarithm of AU infinity minus KEL times T. If you look back, this is what you see. For an IV, I'm gonna say for IV bolus dose. This is not IV bolus now, we're talking about oral absorption or some route that requires. So it doesn't have to be oral, it could be intramuscular or whatever, but usually this model is for oral dose, okay? So this is for IV bolus. We had this equation. Well, without me even having to draw it on the board, y is equal to mx plus b. The intercept from the IV bolus dose on similar people was AU infinity, if you recall. We didn't do a whole big, deep mathematical treatment for the IV bolus dose. I gave you the equation that we talked about, and I drew the graphs on the board in class. So for the IV bolus dose, the back extrapolated y intercept would be equal to AU infinity on similar people. Don't make that mistake here. This is not AU infinity. Okay, look at the equation. So this graph for after the oral dose, his intercept is going to be AU infinity times, what's that, KA? Beautiful, over KA minus KEL. Now I'm telling you already, just as sure as I stand here, that's the y-intercept right there. Somebody on the test or in laboratory today or whatever it may be, I'm gonna say, tell me the value of AU infinity from your y-intercept. Or tell me the value of AU. I'll take that back. Just tell me the value of the y-intercept. And somebody's gonna say, well, that's AU infinity. That's not AU infinity. The equation says that y-intercept is this right here. So we're gonna do this type of graph in the laboratory today. The first thing we're gonna do is I want to make sure that everybody can use the equation. So I'll let you work in groups with it, but we're just gonna make up some values for Ka and KEL and KU and the dose and the absolute volume of those at L. And then I'm gonna have you calculate AU at given time. 30 minutes, 1 hour, 2 hours. We're gonna create a chart, a table. That table is gonna have in it AU values and time values that we're gonna create based on some made up values for KU and KA and KU, some assumed values. We together so far? So we're gonna create a table that's gonna have AU and time. Okay. And then we're gonna plot that data. Okay. We're gonna determine AU infinity, but we can do that from KA and KL. We can calculate T max so we can find out when we're in the postal problem phase and when this situation should prevail. So we're gonna take that made up data and do a sigma minus plot. Am I making sense? And then we're gonna calculate from our sigma minus plot, we're gonna calculate the slope, which is gonna be equal to negative KEL, to see how close we can get back to our original assumed value of KEL. We already know what KEL is. We used it to create the fake data. Does that make sense? Then this intercept right here, well, the y-intercept is equal to AU infinity, on semi-log paper, AU infinity times KA divided by KA minus KEL, KA minus KEL. So what you're gonna do also is, we can read the y-intercept right from our graph that you're gonna make in laboratory today. You can read that y-intercept from your graph, you better be able to. You're gonna set that equal to this right here. If we know AU infinity, if we know KEL, we can solve for KA. We can just rearrange this equation. We can rearrange this equation. So see, this is another thing. Hopefully, if you can do it before lab, that'll be good. Okay. See if you can rearrange this equation. I could do it right now for you, but I want you to do it a little. See if you can rearrange this equation. Let's say rearrange. Rearrange. To solve for KA, to solve for KA. So I want you to just see if you can come up with an equation that says that I'm trying to write an A, but the board is moving and I'm writing low. See if you come up with an equation that says that KA is equal to, if I rearrange this equation, everybody see what I'm saying? Because at first, let me give you the first step, sports fan. Let me give you the first step. The first thing you want to do is cross multiply. So this is why, Autumn said, oh yeah, this is why over 1. So you just cross multiply.
That's what I'm thinking, take the bottom.
So what you're trying to do in algebra, pre-algebra, I think they call it isolate your terms or whatever. So initially you're gonna have Ka on both sides of the equation. But you learned it, yeah, so you can get the equation, so you have just one Ka in the equation, okay? Then you can solve for Ka. Now sports fans, this is urinary excretion data. What I'm trying to show you is that we can use that urinary excretion data to get an estimate for absorption. It just seems so bizarre that I could look at drugs, what's happening over here, to get an estimate of what's happening right here. But you can, okay, by using this methodology right here. So once we do that sigma minus plot, we can take advantage of that y-intercept. Okay. We're gonna know AU infinity, because that's gonna be part of our table that we're gonna create from the fake Ka and K. You know, we're gonna know AU infinity, because AU infinity, remember, is just this right here. So if I assume a dose, if I assume a value for Ku, and the absolute bioavailability F, and the KEL value we're gonna get from the slope of the line, we already know what KEL value is because we use it already to generate our fake data. So here, all we're trying to do, when we do our sigma minus plot, we're trying to analyze that graph and see how close we can get back to the original values that we put in this equation. Am I making sense? We're just trying to see how close we can get back to it. That's called doing a simulation, okay? So when I test you know, the real test or whatever it can be, this is what you might see. But I already know the values for Ka and KEL and all that kind of stuff without analyzing this graph, because I assumed some values in this equation in the first place to give you some data to apply. So that's what we'll be doing in the laboratory today. Question on this, talk to me. Any questions? Now's the time. Questions?
I'm
No?
stuck algebraically. Okay, so.
Well, you got a couple of things.
Okay.
Okay, I can stand up here and go step by step. I'm just trying to get you to work a little bit, okay? So, see if you can rearrange this to come up with an equation with Ka just in one place. On the left side of the equation, it says Ka is equal to whatever. So that's called what? I don't know what they call isolation terms or grouping or something. They had some fancy name for it in the algebra. But we only want Ka to be in one place. So does it collect your terms? I forgot what it's called. Somebody called my name, I heard. Did you bring it? I don't know, you can see right away. I don't even know what the final equation is, but I know how to get to the final equation. You follow me? Okay, we need to have that final equation so that we can calculate the value of Ka. Okay, that's all I have for you today. I'll see you all this afternoon, okay?